so far we have seen that the any control system, that one is our objective. That one is our objective. Just a moment. Which is RS. This one is objective. Hedef. And that one is result. We conduct our study in S domain, but we know that the real life is in time domain. That one is controller. The main purpose of this controller to provide a result equal to the objective, hedef. So that one is error. So error should be 0 or at least very near to 0. This is the main purpose. So if you have that GS is a system including the actuators and things like this. All the electrical, mechanical components are inside GS. Okay. Now, this, of course, if you have any measurement, so the gain of the measurement is also reflected in this system as well. So that is the measuring part. This one, you are measuring output and compare it with the input. Input means your objective, your wish, and then the difference between those is error. In our real life, if you expect to have a very luxury car, for example, Ferrari, for example, you are expecting to buy a Ferrari. This is your objective, but the result, you have only 1/3 of it, 1/4 of the money available. Then you are going to end up with other brand, with a cheaper brand. So in order to gain more money, you are going to make more money to get that one. The error is going to be smaller. So if you earn a lot of money, then you can buy Ferrari, and then your objective is fully satisfied and error becomes 0. Anyway, for our case last week, I don't know whether you have looked at the home assignment, which is a very valuable home assignment. It's a 10 marks, and also explains the detail of the. If you solve it by yourself, then lead compensator could be clearly understood. The controller itself is either adding a 0 to this system or a pole to the system, or both 0 and pole to the system, or adding, for example, for PID, we are adding 1 pole and 2 zeros to this system. So that is the controller. That could be proportional, integral, derivative, and also altogether that one, or lead compensator or lag compensator. Now we are talking about the lead compensator. If we are not happy about the performance of the system, of the control system, then we add a lead controller to this system. Last week we studied that one. We have seen that last week. That is the general system with the compensator equivalent circuit. You can see that it's an operational amplifier circuit, and the output over input is your controller. And we have already seen that the equations are clearly reflect that we are adding 1 0 and 1 pole to this system. And for lead compensator, this one is lead. I'm repeating last week's course. This is lead. This is a lead compensator. Şu A'yı tamamlayalım. Tamam. This is a lead compensator where you are putting a zero here near to origin and a pole which is a bit far away from it. That one, of course, is a lag compensator. Today we are going to discuss lag compensator as well. So last week we have solved this problem and we said that if we have a system like this, it's a second order system, but it's not very nice since it's very near to the j omega axis. And if we solve the damping ratio, the undamped nature of frequency, or real part of the pole, which is this location, that one here, this point, the real part. This is the pole. That is the imaginary part. It's over 3, J3, and that one is 0.5. So angle here is beta, and the cosine beta is zeta. And we have proved that zeta was very bad, and the curve was like this. This is the curve. When you draw step num then, if you get the transfer function first and then write the step num then, you are going to obtain a 60% overshoot, and it was over 10 seconds. I proved that one. I solved it for you. And if you follow the home assignment, you are going to enjoy that. You are going to design a new compensator, lead compensator. Okay, so it's unacceptable. What are we going to do? We have two methods. I explained the second method, which is very simple. What we are going to do, we are going to add 1 0 near to origin. Unutmayın. 1 0 near to origin, and the one pole a bit far away from origin. The rule is this: the rule is that 1 plus GH, which is delta, which is equal to 0. So GH is equal minus 1. So GH is equal to 1, and the angle GH is equal to 180. And also if odd harmonics, odd multiplication or orders of those. Tamam. Yani angle should be 180 degree and the amplitude should be 1. But you are going to add 1 0 and 1 pole. What you did actually, I remember that we were not happy. Just a moment. We were not happy about this pole -1. So we would like to get rid of that one. Instead, we are going to put we are going to put a 0 here. So you select the 0 here. This 0 cancels the pole, but since a new pole, you define a new pole somewhere there, I don't know. We have already solved that problem. So this is a desired pole. So by choosing your desired pole by yourself, by looking at the performance, buraya dikkat. I repeat, it's important. You are selecting those poles by yourself. So when you select those poles, these are your objectives now. When I select ordinary. So your angle now and your zeta is new one. This is objective. But what we are going to do, we are going to start with assigning a 0 on top of it. But the angle here, I don't know how many angle we select. Elle çizeceğim çocuklar. Güzel olmayacak ama yani başka türlü de olmaz. Şu açı, sorry. Aa, hala yazıyor. Üstüne koyayım da yazmasın. Kalemin bir modu var. Temas etmeden, without any touching, is writing, which I hate. Şunu da sileyim ya. Bu ne ya? Not this one. There is a note, Hamza. Can you see the pen? There is a note here. Okay. If I touch that point by mistake, now this angle, let's say alpha, and you are selecting a point somewhere there, okay? And that angle, let's say buna alfa 1 diyeyim, buna da alfa 2 diyeyim. Alpha 1 plus alpha 2 should be 180 degree. So you are actually selecting the other pole. You are selecting the other pole somewhere there, but the angle is going to be the angle here, alpha 2, should be equal alpha 1 plus alpha 2 100. When you select those, you are selecting 1 0. I'm sorry, kırmızıya geçmem lazım. You are selecting 1 0 and 1 pole. That's all. And then you solve it. When you do that, you already add GC is equal KC times 1 plus 1 over T. 1 0 you add, 1 plus 1 over alpha t, and 1 pole. Of course, pole is far away from origin since alpha smaller than 1. That is lead. That's what lead compensator is all about. When you do that, I've solved the problem, so I'm not going to repeat it. The second method I used, that's the one I used. So you can see that this is a selected, that is the selected point. You like it by controlling the angle here, zeta, real part, settling time, maximum overshoot. So you, if you satisfy with those, then you select, you say that this is my objective. Then you get rid of the original -1 on top of it. You put a 0 on top of it. And the angle condition, since this is 120 degree, another 60 degree is giving you another. That's the kalemle göstereyim. So you are actually selecting 1 0 here and 1 pole here. These are the lead compensator values. When you use those, you can calculate GC, KC, everything. I did it before, so you already know that. You end up with my method, the second one. I prefer. It's easy to do that. You are going to end up with this curve. So it used to be 60% overshoot. Now our overshoot is 18% or something like this. Settling time is less than probably three seconds or something like this. It's faster. Settling time. How you know how to calculate the settling time? And also you can draw the ramp response as well. So you can see that in ramp response, our method is slightly worse than the first one, which first one we haven't discussed. If you need it, you can read it in your engineering life. You can read the books. Now we are looking for lag compensator. For lag compensator, by the way, that is the controller, and that one is exactly the same. But here, alpha for lag compensator, alpha is higher than 1. Alpha is smaller than 1. Alpha is higher than 1. But your book instead use beta. If you read the book, he, in order to misunderstanding between lead and lag, he always use beta. Beta is higher than 1. But same network. That's right. Now, the main purpose of the lag compensator is such that, listen carefully, please. You are satisfied, you are happy about your transient performance. Your transient performance means that you are happy about your overshoot. You are happy about settling time, the other parameters, all right. But you are not happy about steady state error. Şimdi in order to remember our steady state error, I'm going to come back to another area. Steady state error. I'm going to review what we have talked, but I'm going to review the steady state error again, okay? if you follow me carefully, I have been thinking always whether you can understand the topic better or easily. I try to make it easier. You see, I spent some time to make it understandable. So follow me, please. So what we need for lag compensator, we are not touching the transient performance. So we are happy about the poles. So if this is the example, for example, that is the example. So when you solve it, you can see that one pole is located here. We are happy. The other one is located here. The other one is located there. And the curve is something like this. So it's in a stable part. We are quite happy about transient. But steady state error is not good. So I'm going to come back to steady state error topic in order to refresh our memories. Tamam. Niye gitmiyor bu? Tamam. Now we remember the steady state error. You remember that. You have error is between the hemen söyleyeyim. RS, your wish. CS is the reality. The difference with those is RS. So this is ES. That is ES. Okay. RS minus CS. Over RS, percentage value of error, with which is equal to 1 minus CS over RS. CS over RS is your transfer function. So when you solve it, you are going to obtain that. It's going to be 1 over 1 plus GS. So as a result, ES error is 1 over 1 plus GS times RS for unity feedback system, by the way, times RS. Steady state error, which is equal to limit time goes to infinite ET in time function. But we know that in Laplace theorem, that means limit S goes to 0 times SES. You already know that. So it is result is this limit S goes to 0 S over 1 plus GS times RS. Of course, RS might be, you tell me, RS might be step, RS might be ramp, RS might be parabolic. Okay. So of course your steady state error should obey the behavior of the RS. RS is important. Of course, GS is more important than anything else since the system is represented by a GS. However, RS is also important. So they are defined to make it easy. Although by hand, you can easily solve the above equations and you can obtain the steady state error. But in order to make it simple, they call it static position error. This is a step response, by the way. The steady state error for the system of the system for a step input. And the Kp is static position error. They call it static position error. Kp here, you can see that statistic, this equation I already give you. And if you put the equation here, so you end up with 1 over 1 plus Kp. So Kp burada is equal S goes to 0 Gs. G0. For type 0 system, type 0 ne demekti? Şurada küçük yazacağım. Çok küçük çünkü. Biraz büyüteyim en iyisi. Type 0 burada bir S var ama üzeri 0. Yani 1. That is type 0 system. Type 1 system S to power 1 and the type 2 system S to power 2 or S square in other words. So let's make it smaller now and look at it all together. So for static position error, your type 0 system is K. For I'm sorry, Kp is equal K and ESS is equal 1 over 1 plus K. Bunu ezberlemenize gerek yok ama bu slaytı hatırda tutun, bu slaytları. Don't memorize those, but don't forget those slides. This is static velocity error. Static means steady state actually. Velocity error. This one is kV. The earlier one was Kp. Now this one is kV. Kv is equal to, of course, the same equation like this, but in that case, input is ramp, therefore is instead of 1 over S, it's 1 over S square, so it's SGS. So for type 0, error becomes infinite. Very bad. For type 1 system, it's 1 over K, and type 2 or higher order, higher systems type in with respect to type is 0. So this KV, K, and also this is a ramp response. Ramp actually associate with the speed, but parabolic input associate with the acceleration, since it's another derivation of the speed. Static position is step. Derivation of this one, of the step, is ramp, and derivation of the ramp is acceleration. So acceleration constant also is calculated like this one. In that case, is power to 3 here. So these values are, we are going to use those Kp, Kr, and things like this, since the log compensator actually based upon this purpose. We are quite happy about our compensation as far as transient performance is concerned. So it's a nice overshoot we have, a very small settling time or acceptable settling time we have. We are happy, but we are not happy about steady state error. So what are we going to do? So I leave this one. This table, you remember, bir table var. Tamam mı? Bu table işinize yarar. That is the table. Don't forget that one. For step input, for ramp input, and for acceleration input. Parabolic, ramp, speed. That one speed. That one is position. Okay. Bunu niye böyle yazmış? Hayret. Ben olsaydım bunu mesela position derdim. Buna speed derdim. Buna acceleration derdim. Dememiş. Step, ramp. O zaman buna da parabolik yaz. Anyway, ama siz anladınız. Yani step means position, ramp means speed, and parabolic means reflex acceleration. Okay. Now we are going to come back our original lock compensator. That was the compensator itself. However, in that case, R1C1, can you see that? Follow my cursor. R1C1 is smaller than R2C2. However, for lead network, R1C1 was higher than R2C2. It's opposite. Your book, instead of alpha, your book is using, bir dakika, şu şeye bir daha bakalım. For now we are designing a lag compensator, so we are going to put additional pole near to origin, and that one is far away from origin. Now, if you write down the equations, which obviously the same equation we are going to have. Bakayım nereye yazayım onu? Lag'a geleyim, lag'da yazacağım. Yeah. Şimdi lag compensator için GC mümkün mertebe bunun üstüne yazacağım çalışırken rahat edin diye. Çocuklar 5 punto kalın. Moment inceltelim. Evet. GC is equal to Kc times 1 plus 1 over T over 1 plus 1 over beta T. Now this is that is the zero we are adding. That is the pole we are adding. We are adding 1, 0, 1 pole. But since beta is higher than 1, so actually the point we are adding the zero we are adding is away and the pole is somewhere there. So we are adding a pole and we are adding a zero. Şimdi probably you may wonder why I give them very close. Since we are happy about the transient performance, so pole and zero should be very near each other, and near to origin. Near to origin. Very near to origin, and it should be very near to each other. Near, very near to each other. If it is very near to each other, it's not going to change the angle. So angle should remain 5 degrees, very near. Not, you are not going to change it. But in order to reduce the, so I'm going to continue. Did you understand that one? I'm going to clean that page and I'm going to write something additional to this one on top of it. Pole and zero should be very near to each other. That means you are not actually shifting the system. 1 point. The second one, it should be very close to the origin. I'm going to explain it why. So for this equation, T, the equation here, Kc times S plus 1 over T over S plus 1 over beta T. So that is GC. Now T is equal to R1 C1 beta T is equal R2 C2 beta is equal to R2 C2 over R1 C1, which is higher than 1. And Kc, onu da şuraya yazayım. Sığmaz. Kc, şurası daha iyi. Kc is equal to R4 C1 over R3 C2. Şunu silelim. Belki buraya bir şeyler yazarım. Şimdi the main objective to provide a lead compensator, that means pole is very near to zero, almost zero, and zero, sorry, pole is very near to origin. If sometimes I use zero for origin, of course it is it's zero too. However, it's origin. Pole should be very near to origin, but also the zero should be very near to pole as well. I'm just reading a material here. Just follow me. Consider the problem of funding suitable compensation network for the case where the system exhibits satisfactory transient response characteristics but unsatisfactory steady-state characteristics. Compensation in this case essentially consists of increasing open-loop gain without appreciably changing the transient response characteristics. This means that the root locus in the neighborhood of the dominant closed loop poles should not be changed appreciably. You understand, as I told you before, we are not going to change the original poles and the operating points, but the open loop gain should be increased as much as needed. This can be accomplished if the lag compensator is put in cascade with the given feed forward transfer function. Evet, ben kendi cümlelerimle anlatsam daha iyi olacak. Yalnız şu cümleyi de okuyayım. To avoid a big change in the root loci, root locus, the angle contribution of the lag network should be limited to small amounts, say less than 5 degrees. So lag changes, the angle changes should be lower than 5 degrees. From that point, S1 plus one over T and S2 plus beta T are almost equal. Ne demek? I'm adding a zero, but I'm also adding a pole, but these are very near to each other. Very, very near. That means angle condition aşağı yukarı 0. Amplitude is equal to kg. That means your amplitude is going to be kc, I'm sorry, your amplitude, and the angle should be as low as possible. Bir example yapmadan olmayacak bu iş ama bir tane daha slide vereceğim. Dedim ya, steady state error is important. So for steady state, by the way, static velocity error constant which is kV. You remember we reviewed that one. kV is equal to limit s goes to 0 SGS. We are just reviewed that one. So for that case, then what's happening actually? kV, which is equal to, when you compensate it, limit s goes to 0 S GCS, GS. So you add the compensator here, which is equal to that one is KV olduğuna göre limit S goes to 0 GCS times this one is KV. O da eşittir. Bakın result burada. KC the controller of the lead lag compensator beta times KV. Şimdi bunu bir kırmızıyla çevirelim. Bu sonuç bizim için önemli. Çocuklar, static velocity error, a new one. Buna şapka koymuş şöyle. KV diyeyim. Sonuçta yenisi çünkü. KV, a new static velocity error. Static velocity error ne demek? Velocity means speed. So if you are controlling the speed, your speed, steady state value of your speed should be as low as possible. How could you achieve that one? I have a question. How could you, this number should be as high as possible, since it appears in the denominator. You remember that this 5 minutes ago or 10 minutes ago we reviewed our steady state error constant, so this appears in the denominator, so it should be as high as possible. How could you achieve that one? How could you achieve this? Neyse, bulut girdi. Benim de gözüm alıyordu. Sizinkini de alıyordur belki. Şöyle geçersem, evet, camın önüne. Ne diyorsunuz? Nasıl sağlayalım? How could we achieve that? Making KV higher. Generally speaking, beta is the parameter here. Beta is selected 10. Okay? For lag compensator, beta is selected 10. Tamam. Bakalım ne geliyor şimdi, görelim. Problem gelecek. Evet. Now we have a problem. Problem is this. How do you find those poles? How do you find those poles? Düşündünüz mü hiç? Nasıl bulmuş, koymuş oraya? Tamam, root locus yazmış, num'den root locus demiş ama have you ever thought about that? Çok hızlı yapayım çocuklar. Zamanımız az. Sömestr bitiyor. TF is equal 1 plus G. O da eşittir 1.06 over 1 plus 1 over 06 over that one, which is equal to 1.06 over, şimdi bakalım ne oluyor. Ezbere S kare, S küp bir kere geliyor. S küp plus başka ne geliyor? 2S bir geliyor. Bir S bir geliyor. 3S. 3S kare. 3S square plus ondan sonra 2 kere 1 2 2s artı 1.06. Transfer function bu. If you write num noktalı virgül then eşittir noktalı virgül. So root locus num then is going to draw that curve. Tamam? And then you are going to obtain those as well. Bakalım ne yapmış? Şimdi arkada yapmış çünkü. But we are not happy about this one since steady state error is not good. Bakalım öyle mi? Ha, kafadan seçmiş. Beta is 10. You remember beta 10 is a good number. One of the point you shouldn't forget that if you use a log compensator, you are going to use beta. You are going to select beta equal 10, and the poles and zeros should be very near to origin. And this one is that one, and the Kc here is obtained 0.966. Hemen göstereceğim. Burada bakın çocuklar. Bir öncekinde bir geri gideceğim. Oradan gidilmiyor. Burada bunu devam etmem lazım. Kitapta yazmış. Onu vereyim size. TF is equal to 1.06 over S plus 0.33 minus J 0.586 sorry pi 8 0.86 times S plus 0.33 plus J 0.586 bir üçüncü pol daha var. S plus bu real 2.338 uzatmayayım daha fazla. 8. Şimdi biri burada bakın. Diğer ikisi the other two are located. One of them is this one over here. The other one is over here. So the poles could be found and obtained by using MATLAB. You can obtain or you can solve those and you can obtain that one. So the dominant poles are actually these two. That one, this one, and this one. These are dominant poles. So what you are going to put then, Kc for zeta, burada for the zeta, it's I'm looking for from the book. I'm not happy about this one really. It's not very low. And the omega n is equal to however kV, which is calculated 0.57, sorry, 53. kV should be 5 at least. At least 5. What am I going to do? You remember our equation. kV multiply with beta. So beta 10 is selected. When you select the beta 10, then it's going to be end up with this one. I'm sorry. So the very near to zero, very near to origin, but this one is even, you may call it origin. You are adding another pole to this system. Okay. For this system, when you solve the system like this and then draw the curve, şimdi curve'leri göstereceğim. New closed loop, sorry, new closed loop is not changed. You can see that. However, steady state error is 10 times smaller than before. And if you look at the amplified value, what we are actually doing, buraya yazacağım bunu. Bunu iyice küçültmem lazım. Çok büyük. S plus so we are adding 1 0, 1 pole. We added pole is something like original equation'a da bakalım. What was the original equation? Original equation was, şuraya yazıyorum onu da. G S was equal to 1 point, not the transfer function. I'm just writing the GS 1.06 over S plus 1, değil mi? Evet. S plus 2. Şimdi S plus 1 blue Burada bir tane S0 da var. S0. Ondan sonra e, e, diğerlerini yani küçültmem lazım. Şimdi buraya I add bir pol daha ekliyorum. Bir pol daha ekledim üstüne. Bir pol daha ekledim. We have two poles. But also we add a zero here. So what's happening? Actually, the root locus is moving like this. And these are dominant poles, by the way, very near to J omega axis. But at the end, one of them is end up with this direction, end up with this one. So end up with zero. Küçül kardeşim, küçül. Heh, tamam. Artık anlaşılır hale geldi. The other one is moving and the other one is coming from this point. So shift it like this. Şimdi biraz küçültünce göreceksiniz ne olduğunu. You are going to see clearly what's happened. You can see that it's all located here, but this pole is coupled with the other pole here, and then they, without changing the root locus curve, however, increasing the velocity error constant. In other words, velocity error is reduced by 10. Yani onda bire düşüyor velocity error. Reduce velocity error. Increase velocity error constant by 10. Beta 10 çünkü. Velocity error'den kasıt ramp response error. Sanıyorum anlaşıldı. Şimdi bir ara vereceğim. Aradan sonra bunu tekrar edip bitireceğim çocuklar. Kapatacağım olayı. Tamam mı? Şimdi dalga şeklinde göstereyim. Gördüğünüz gibi şeyde ramp response'da çok az bir değişiklik var. Yani compensate ettiği zaman biraz daha lehine bir durum var. And şeyde de çok az bir değişiklik var. Transient'te. Bundan sonra bir lag lead compensator var. İkisi bir arada. Lead'in ne olduğunu you already know how to run lead. You already know how to run lag. Lead lag together is also acting like this. So I'm just going to give you break here. Break. Şimdi saat 10 geçiyor. Pardon. Evet 10 geçiyor. 10:25'te buluşalım. 10:25. Break. All right. See you then. Yes, I come back. Hello again. Now we are starting. I'm just going to review the lag compensator and lead compensator. For lead compensator, uh, the we are not if we are not happy about the transient response, we add a zero M pole to this system, but zero is near to origin and pole is far away from it. And how could we calculate? We several times repeat that one, and you have a home assignment. So please solve those home assignment by yourself. Don't take to anyone, okay? Then you don't understand what is going on there, okay? I always prefer the easiest way. The second method, there are two methods in your book, but the second method is very easy and gives a reasonable good results. That's what lead compensator is all about. However, if you are not happy about the steady state error, then lag compensator is also needed. Or if you are happy about your transient performance, the steady state error, sorry, the transient response, the maximum overshoot, settling time, and if you are happy about those, then it is. However, if you are not happy about the steady state error, then you are going to use lag compensator. For lag compensator, beta is approximately 10 is selected. That means your steady state error 10 times reduced. But you can select 11 even higher than this. But generally speaking, 10 is a good one. And you are going to add one zero and one pole. But in that case, pole is almost equal to origin, very, very low pole, almost zero, almost origin, the value. And also a zero is very near to this. Since these two are coupled, we have already seen in our curve that in this curve, we have already seen that these two coupled here, I'm going to make it bigger and explain it for those who recently come. So what we are adding, you can see that we are adding a pole here and zero here, but the one pole was already over there, and these two poles are gathered. One of them is moving in this way, the other one is moving in that case for closed loop system I'm talking about, and the journey ends in zero. One of them ends in zero, the other one couples with the other pole, and the your root locus curve is not changed. You can see here is almost the same root locus curve is could be seen. This is what lag compensation is all about. Now I'm moving. And also we have seen that the compensation compensated system reduced the steady state error for ramp response, and step response slightly worse than uncompensated case, of course. Transient is affected. That's the end of your chapter. Now I'm going to move to another one. PID controller. Now, this is a completely different topic, and it is the last part of our course. I'm going to come back to Bode plots and frequency domain solutions, but first of all, I would like to give this one before the last week. Last week is our, next week is our last week. So you have to learn about PID controller as well. Of course, you have learned how, but you are going to learn how to design with your PID controller. Just review the PID controller action. You remember that is PID GC. That is GC, which is PID. And this is the plant. Although a plant is given small here, it has all the system equations and also the, if there is any actuator, which mainly there are actuators, could be heating system, could be cooling system, could be position control of the robot arm, or could be speed control of the electric vehicle. Whatever it is, there's always an actuator over there, electric motor mainly, or blower, heater, or process, chemical process, which I don't know the equations of it, but in any chemical system, control is also very important anyway. So what we have here is a PID controller. PID controller means your controller actually adding, come back to the original one, a proportional constant. Proportional constant produce output which is proportional, multiply with the proportional constant, output is equal to input times ET times error times KP. However, integral controller is integrate the error and then gives you the output. Of course, never forgets, integral controller never forgets the error, integrated since. And also derivative controller gets the derivation of the error, so it predicts the future oscillations and things like this beforehand. So these three together, we already discussed the effect of those, but now we are going to design it. We all know that the yazmamışım buraya. Bunları ben yazdım. Just a moment. Beş punto bizim işimize gelmez. Heh. Şimdi buradan KP bracket one plus plus so TI is equal to Kp over Ki, and Td is equal to Kd over Kp. So when you write down those equations and continue, you end up with this equation here. Kp bracket 1 over 1 TIS. That one here is a Ti, can be seen. Plus TDS, or I have already proved that one. Kp bracket 1 TIS plus TITDS square over TIS. That means you are actually adding two zeros to this system. You are adding actually two zeros to the system and one pole. Okay. PID means you are adding two zeros, one pole. Lead compensator and lag compensator, we were adding only one pole and one zero. Here we are adding two zeros and one pole. But the value of those is very important. Yeah, that's right. Kp is proportionality gain, integral time, Ti, Kp over Ki, and Td is Kd over Kp. All right. Now, there are two rules. The first Ziegler-Nichols rule, these Ziegler-Nichols rules are established many years back, but still used. Since you have number of infinite values to be defined, you are going to define three values, by the way. Three values. One of them is Kp, the other one is Ti, the other one is Td, or the constants. Now, if you give a step input to this system might be giving you moment. For example, it might give that kind of solution. Or it might give even solution like this. These are not acceptable. First Ziegler-Nichols rule is not applicable those. It should be, an output should be something like this. If you have an output like this, that means no overshoot, then it's acceptable. So, for example, overdamped system and things like this. That is the answer. So if you have a curve like this, there's a tangent line. There's of course a curve changing here. This is the point where if you draw a tangent line parallel to this, and then the crossing the zero axis here, time axis here, horizontal axis, the distance is L. L is a delay time, and T is the rise time, let's say. T, and if you manage to measure L and T, I start from very beginning. you are applying a step function to this system, and you are obtaining that kind of this kind of solution. And then you measure L and T, and then use this table. For proportionality constant, you already measure T and L, use that one. Ti, you assume Ti infinite, Td 0. Ne demek Ti infinite? What does it mean? Ti infinite. Bir dakika, şurada tanımladık. Şurada var. Ti infinite means Ki Kp over Ki is zero. Ki is zero ne demek? Ki is zero ne demek? Nerede o? Ha. Ki is zero demek I don't have integral controller demek. If you don't have integral controller and Kd is zero, also if you don't have any derivative controller, only the proportional controller available demek means that. So that means you haven't got any integral controller and you haven't got any derivative controller. For Pi, you have, of course, integral controller as well. So what Kp value and the Ti value is given. So this is the chart, or this is the table designed and developed by Ziegler-Nichols. They published it many years back, still used. For PID, however, whatever you measure L and T here, you just of course you might use simulation as well. Then you obtain that one over 2 T over L, 2L, 0.5 L. Now I have a question. What am I going to do if you have oscillation like this? Which quite often we have oscillations. If you have an oscillation like this, most likely our Root-Locus curve buraya yazmayayım. Bu kafa karıştırır şimdi. Sonradan çalışanların kafası karışır. Ben bir temiz sayfa açayım. Oscillations. If we have oscillations like this one, for step response, what am I going to do? This is time. This is ft, any function. Step response. If you have a step response, what am I going to do? Most likely, your system is something like this. Most likely, your root locus curve is something like this. This is S-plane, by the way, and these are the curves. Most likely, you have one pole is located here, another pole is located there. These two poles couple, and the curve is something like this. And there is another parabolic pole here. So what you are going to do in that case for the second Nichols rule, Ziegler de vardı. Rule, obtain KCR. KCR şu nokta. Of. Yine kalemin nobuna yanlışlıkla basmışım. Şimdi sileceğiz, ortalığı berbat edecek. Şimdi hasar tespiti. Gene hasar, gene hasar. What are we going to do? If you have a system like this, you are going to first obtain those points. One of them is this one. The other one is that one. The value of K is equal Kc, critical K value, Kc. If you obtain K value, what would be your time response? Output for step. Who is going to draw that curve? What kind of curve do we have for step response if K is equal Kc, critical value? Who is going to contribute in our classroom? Ne diyorsunuz? Hiçbir şey söylemiyor musunuz? We have 15 students in our classroom. What kind of response do we have? Düşünün bakalım ya çocuklar. Vaziyet kötü. Bir tek şimdi I don't want to be monologue teaching. Monologue teaching is a very dangerous thing. Nobody contributed. Nobody say anything at all. What kind of response to this one? This is a critical. This is a critical critical K value. K niye böyle olmuş? Neyse rengini siyah yapalım. Is KC. Critical K value. Okay, solution is going to be something like this. It's going to be oscillating. And of course it has a period and other values. So is it clear now? So if you have a oscillation like this, that means your system has got a possibly curve like this, and if you increase K value, you end up with this point. And if you find that point, then your solution is going to be something like this. Ziegler-Nichols also giving you some points, but before doing that, how could you find that K value? Çocuklar unuttunuz mu ya? İmtihanda soracağım bak. Raut-Hurwitz. If you employ the Raut-Hurwitz, you can obtain the K value. Geri dönüyorum. KC. Şimdi iki şey arıyorum. Burada. Two things is important. One of them is PCR period. The other one is KCR. These constants P period şuradan sıfırdan başladı. Tekrar sıfıra ne zaman indi? Burada bir tam periyot. Şöyle bir. Tabii iyi çizememişim. Onun için. İkinci periyot. Demek ki şurası. Bir periyot. Neyse şu iki tane pik arasını ölçeyim de şöyle PCR. Periyot. KCR critical K value. Şimdi dönüyorum artık slaytlarınıza. Burayı kendimce sizi alıştırarak açtım. That was our starting point. That's what PID is all about. And this is the first Ziegler-Nichols rule, where you can get this curve and measure the L and T, or if you cannot make a measurement, you can simulate the system as well. And then you are going to put those values for measure TLL. Now, the second Ziegler-Nichols method, uh, increase Kp until roots are on the j omega axis. This K value is called KCR. So KCR is a function like this. And of course, the solution step response is not like this, but doesn't matter. PCR is the period of it, and the KCR we have already obtained. And then this is the second Ziegler-Nichols method table. For proportional controller only, you are going to use that constant. For PI controller, you are going to use that constant and this constant. For TI, you are going to use that value. PCR already measured, KCR already obtained, and the PID here is 0.6 KCR, 0.5 PCR, and 0.125 PCR. So these values, if you use those values, you can start with it's a good starting point, not the best one. I repeat, for P, I, and D constants, these are good starting points, not the best ones. There's a problem now. We are going to solve it together. What would be the GC PID controller for this control system? Can you draw the root locus of it? I can easily. One pole is S equals 0, origin. The other one is, let's say, -1, another pole. Another pole is -5. 1, 2, 3, 4, 5. Şöyle buralarda bir yerde. -5. We all know that the root locus curve is going to be something like this. And for k equal infinite, and for k infinite, it's going to change the closed loop poles. For okay, so this is imaginary axis. So any pole would be nice, but we would like to improve that curve. We would like to get better. So what we can do, we can add 2 zeros and 1 pole. 1 pole is in origin anyway. Was it on origin? We'll see. Did you understand the problem? This is the root locus curve. Now we are going to we are going to employ the second Ziegler-Nichols method. But how could I find those for second Ziegler-Nichols method? He says we can add two zeros like this and one pole like that with a constant like this. How could we find that? All right. So you follow me. Tabii ben bunu kağıtta anlatsaydım çok daha iyi olurdu. Ama mecburen böyle yapacağız. So what we are going to do, we are going to start from very beginning. Çocuklar bir 5 dakika ara. Ten minutes break. Ne zamana kadar? 11:15. I will come back 11:15, okay? Evet, let's continue. Now, this is the problem we are going to look, and what are we going to do? This kind of system uh, most likely is going to be oscillatory. Therefore, we most likely we are going to use second Ziegler-Nichols method to this system. So I'm just going to open a new page. Oh, look at that. What a mess. The problem here is this. CS over RS is equal now. That means s to power 3 plus 6s squared plus 5s plus kp. Now what we are going to do for the second Ziegler-Nichols method, we are going to obtain the KCR. In order, that is delta, by the way. That one is delta. So apply Routh-Hurwitz method. Here, the first coefficient is 1, the other one is 5, and this one is 6, that one is Kp. 6 times 5, 30, minus Kp over 6 is 30 minus Kp over 6, and that one is 0. This one, follow my cursor please, that one multiplied with Kp minus 0 divided by this one is equal to Kp. So that one is Kp here. So we know that this should be plus, this is plus, this is plus, this should be plus, this should be plus. Therefore, Kp should be smaller than or equal to, of course, for this case, 30 and 0. oscillation occurs. Çok kötü çizdim, bir dakika. Bunu silmem lazım, artık olmaz bu kadar da. KCR which is equal to 30. We already obtained KCR 30. But what are we going to do? We need another one. Şimdi buraya KCR 30'yi bir koyalım. Don't forget that. What about the other one? The other one is a period. So S3 S equal J omega koyalım. Madem ki since it's on the J omega axis, so delta is equal to, at this point, J omega power to 3 plus 6 J omega square plus 5 J omega plus Kp. Kp 30. 30'yi de koyuyorum. I put 30. Which is equal to 0. Delta is equal to 0. So I continue. J omega power, J square is minus 1. So minus J omega power 3 bir dakika. Power 3, tamam. Devam ediyorum. Continue. Of. Siz de görüyor musunuz? Devamlı bir şey çıkıyor. Bana yazmama mani oluyor. Şimdi de düzelmiyor bir türlü. Bir dakika. Ha, gitti. Evet, devam ediyorum. Şimdi 6 J omega square minus'tır bu. J square is minus 1 biliyorsunuz. J square is equal minus 1. Ondan sonra o zaman bu da minus 6 omega square plus 5 J omega plus 30. Bu bakın neye eşit çocuklar? Bu 6 times bracket 5 minus omega square plus J omega 5 minus omega square. eşittir 0. What makes this equation equal to 0? Şuraya köşeye koyayım, sonra öbür sayfaya geçeceğim zaten. Buradan omega square is equal to 5. Omega is equal to square root 2 times 5. Şimdi omega'yı bulduk. Bize ne lazım? What do we need? We need a period. So I clean this page. I repeat. We first write the transfer function. Then, of course, we obtain the characteristic equation. And then we employ the Routh-Hurwitz method. With this method, we obtain that the KCR is equal to 30. And then we put characteristic equation Kp is equal to KCR 30 and write since the point here is j omega, the value here is j omega. This is j omega. That is minus j omega. So j omega is going to satisfy this equation. We write the j omega equation here. Sorry, delta characteristic equation for this pole. J omega here. And j square is minus 1. At the end, we obtain that omega square is equal to 5, or omega is square root of 5. Now I'm cleaning this page and write here that KCR is 30, omega is equal to square root 2 times, square root 5, omega eşittir 2pf or 2p over t. From this point, t is equal to 2 pi over omega. Buradan t dedi pi, kitabınızın şeyine sadık kalarak yazıyorum. PCR, buradan PCR eşittir 2pi over square root 5, o da eşittir 2.8, 2.81. Şimdi table, Ziegler, Nichols. Table'a bakıyoruz. Kp is equal to 0.6 times KCR. Ti is equal to 0.5 times PCR, and Td is equal to 0.125 times PCR. That one is 18. That one is 1.405, and that one is 0.3514. GC in general, bakın şu denklemi yazayım buraya. Başka renkte yazacağım kolay olsun diye. Onu da siyah yazayım. GC is equal to Kp over 1 plus 1 over TIS plus TDS, which is equal to GC is equal to 0.6 KCR over 1 plus 1 over 0.5 PCR times S plus 0.125 PCR times S. Parantezde kapatacak şeyimiz kaldı. Yerimiz. Tamam. GC, in other words, GC is equal to 0.075 KCR times PCR S plus 4 over PCR square over S. So that is the final version. That's the final version of our so let's come back to the blue curve again. Write down here. For GC, is equal KCR 30 times PCR. PCR kaç çıktı? 2.81, 2.81 times S plus 4 over PCR is equal, artık onu direkt yazacağım. Kontrol edeyim. 4 over PCR. PCR'ı kaç bulduk? 2.8. Peki nasıl oluyor 4 oluyor burası? 1.4. Ha, karesi. Burada bir şey var. 4 bölü PCR. PCR bizim kaç çıktı? PCR 2.8. 4 bölü 2 tamam. 4 bölü 2.8 tamam. Şimdi oldu. 4 bölü 2.8 4 bölü 2.8 şöyle şöyle 2 tane kare karesi bölü S. O da eşittir. O şuraya yazıyorum. 6.3 3 2 2 3 S plus 1.4 2 3 square over S. What is your opinion now? What did I do? Or what did we do? We employed, I'm going to ask a examination. I'm going to ask you an examination question for this. So follow me carefully. What we have done, first we have obtained the oscillation. We employed the second Ziegler-Nichols rule. We obtained the oscillation. Uh, so the oscillation period we obtained, and we obtained the K value which caused the oscillation, the limit on J omega axis. Obtain that one. And then we employ the second Nichols, Ziegler-Nichols chart. Look at the chart. It's already here. So we obtain Kp, Ti, Td. These are the equations you don't have to memorize. Either use this one or that one. I prefer that one. So I put this one and I obtain the added value for controller. We are adding double zero for 1.4 and 1s. Okay. Buraya kadar tamam mı çocuklar? Is it alright for you? Valla ödev de vereceğim ha. Söyleyeyim size. Şimdi bir tane şey, I have already given the lead compensator home assignment. This is going to be your last design. These design homeworks are 10 points, by the way. So two 10 points makes 20. Another 5 makes 10. So it's altogether home assignments, design plus design is 30. Your midterm exam is 30, so it's 60. Final exam is 40%. All right. So I continue. We are going to add 2 zeros and 1 pole. I come back to our original slides. We use that table, Ziegler-Nichols second method, P proportional constant, integral constant, and derivative constant we used, and we obtained, we employed this problem, we solved this problem, and we obtained that one. You remember this. I already calculated this one here. So now we are adding this one to, we are adding this controller to this system. What's going to happen? The of course, when you multiply this, you end up with 60% overshoot. And I don't know, but it's, I think, somewhere 10-second settling time. It's not very good. I'm going to come back. You have to understand what's going on from this point of. So for this new system, CS over RS is going to be 6.3222, sorry, the last one is 3, S square plus 18S plus 12.811 over S to the power 4 plus 6 S to the power 3 plus 11.332 S square plus 18S plus 12.81. So this is our transfer function. So what am I going to write here? Num dikdörtgen bracket içine alıyoruz. Biraz daha yukarıdan yazacağım. Sorry. Num 6.32 boşluk 18 boşluk 12.81 noktalı virgül den eşittir 1 boşluk 6 boşluk 11.32 boşluk 18, 18, boşluk 12.8. Step num'den bir de grid koyalım bakalım şuraya. Title da koymuş ama artık title öğrenirsiniz. Step num'den dedikten sonra zaten çizer. When it writes the system, it's going to be something like this. Are we happy? No. But we already employed PID system to this system, and now we are going to get a better tuning, fine tuning we need. For fine tuning, what are we going to do? Of course, we are going to do something further improvement. We are not happy about this one. Sorry. Since oscillation is too high, we have to get the, let's say, less oscillation. Less oscillation. For example, KP moving double zero. Şimdi bir saniye. Bir saniye. Önemli bir nokta var burada. Hiçbir yerde şey çizilmemiş. Bir dakika. Bakayım çizili mi bir yerde. Çizili olması lazım. Tamam. Bakın. That is the case which we obtain, and we can see that our operating point here is this. But we also see, ne görüyorsunuz çocuklar? Biraz zaman vereyim size. Let's have a look at that curve. What do you see? This is Root-Lacus curve, and this is the second Ziegler-Nichols method. The first attempt, we calculated TI, KP, TI, TD. And we employed that, and we draw that curve. What do you see from that curve? Are you happy with that curve? No. Since we have already got step response, and we have obtained that step response was very bad. It was 60%. Yeah, when you write the step MATLAB statement, you obtain that one. That's very bad. 60% overshoot is unacceptable. What are we going to do then? And while we are looking for this one, you can see that slope is always 0.3. So you cannot reduce without changing the curve, you cannot reduce the overshoot. Instead, that double zero should be shifted to this point. Bakın double zero burada. Kaçta duruyor? 1.4. Now if I shift that double zero to near to origin, then it's going to be much better. This is what I should do. If you shift, buraya yazacağım. Shift zero near to origin. For example, 0.65. Kp, of course, Kp on 8. So it's going to be GCS is going to be 18 times 1 plus 1 over 307 77s plus point 769, which GCS is equal to 13.846 S plus 0.65 square over S. When you write this one and solve it and draw the step curve, you are going to end up with this curve. This root locus, this is your new root locus. Okay. Of course, you directly put, biraz büyüteyim. You directly give 0 here. What's happening? The one of the S here is already over there. One of the S I added with PID. I have two S's. So 2S is moving like this. And then, of course, we have two zeros here. Two zeros just couple with these two zeros, the two origins, and then two poles here, and two zeros here. You can follow my cursor. You can see my cursor, can't you? Oh no, you can't. I repeat. Now we are adding one pole here, but we have already got another pole over there. So we have two poles located origin. And we are now adding two zeros very near to origin. So these two couples actually, and they combine like this and cause this curve. In the meantime, that pole here, -1, nerede o? Bu, that one, and -5 now thinks that it's a second order system, and then these two combines that equation. Of course, while you are changing K value, you are going to obtain the best K value here, 13 or 30, something like this. And of course, the waveform is going to be much better. Bu ne bu? Bunu istemiyorum. So this is our final case. I'm going to give you another home assignment. Next week, I'm going to repeat that part. Probably while you are trying to do this second home assignment, second design assignment, you are going to learn more. And next week, we are going to discuss it again. Okay? So I start from very beginning. Only 3 minutes I have, or maximum 5 minutes. Listen carefully. Now, for design of a PID system, of course, we all know that we are adding two zeros and one pole. But those values, Ki, Kp, Kd, are important to define, and it's difficult to define those. Ziegler and Nichols is giving us a hint. If your system is not oscillating, then you are going to get this one and measure or calculate L or simulate and to obtain T and obey that rule. PID should be selected initially. These are initial values. Be careful. Not the optimum values. But initial is very important. In order to start with the roughly correct values is important. And now what we do in second Zignal method, we actually oscillate the system. We increase K and we obtain the oscillation point and we measure the periods. We already obtained the K value which causes oscillation. Then we obey that table. 0.6 kcr, we already obtained kcr, and I solve a problem for you. And this is the problem I solved. And you can see that, of course, it's solved in your book as well. If you reach the book, you can read it in detail. One pole is located S, the other one is -1, the other one is -5. When you solve it, then you are going to obtain the K values, and then when you add those K values, you end up with this system. This is your PID, added PID controller. That PID controller with and together with the system, you end up with this num den and step num den grid. You end up with that terrible waveform. 60% overshoot, more than 10 seconds. It's not very good. So what we should do, we should shift our double. We should shift our. This is the original starting point. That double zero here. If I shift that double zero very near to these double poles, so these two couples, and then the -1 becomes free, and minus the 5, these two couple and draw another line. So that is the basic principle of it. You can see that these, when you shift the double zero to near to origin, then these two couple here, and then you end up with very nice curve, whatever the K you can prefer, but it should be something like this. Okay. All right. Thank you for listening me. Don't go away. I'm going to take attendance list. Yusuf, Yunus, Raid, Omar, Mahmud, Halil, Hüseyin, Hamza, iki tane Hamza var. We have two Hamzas. Ali Umut Terzi, Ahmet, Adel, Abdurrahim, Abdurrahman. So I think I've got that one. Just a moment, don't leave. Seyit Hoca is already in the system, so probably is going to continue. But Seyit, istersen biraz dinlensinler. Zaman ver istersen.
Tamam
Sensiz
hocam,
zaman.
10 dakika verelim hocam o zaman.
Ver.
Tamamdır hocam.
Okay. You have 10 minutes break. Yes, Buradayım, söyle. I'm listening. Who is asking a question about another course? Probably is science, technology, and ethics. Yes, I should do that. Yes, of course I should do that. But I haven't decided. Probably during the next, uh, I don't know. I don't know. Next next Friday we talk. Okay. Okay, Omar. Follow my homeworks. Okay. Homeworks mean design problems. I'm going to give you another design problem for you. Okay.
Hello, everybody. We're gonna start the lab now. Is everyone here? Yes. Okay. Okay. So did you did the homework last week? I gave you. Choose a system. Find the transfer function. Steady state. Step response. Yeah. Okay. Send it to my email. All right. Your file. I'm gonna write my email here. It's my email. Send your homeworks to my email. Maybe I'll upload another homework for this week. Will be last homework. Okay, let's start with root locus. How we find the poles and zeros. Today you learn about root locus, right? The zeros, the poles, how to find them in a system. Okay, let's define our system first. Okay. So for the root locus, we just use our locus, all right? This function will find the root locus of your system. First, you define your numerator and denominator. And in the root locus function, inside you can just write your numerator and denominator, and it will plot your root locus diagram. And you're going to define here v vector for the scale of your graph. And then let's say 6. Okay. And then v axis. Okay. And then you define your axis. It will be square. You want our graph to be square. And then you can add your grade and your title. Say root locus. Now you can run this section. Oh, v equals to. I forgot that. Yeah, this is your I'll forget another. Okay, this is your root locus, your poles and your zeros, as you can see in the diagram. And then with the v-axis, you can scale your graph here, imaginary axis and real axis. And with title, you can write your root locus name here. So this is your system, or you can define it like in here too, just root locus of your system in another way. Like you can just transfer your function here, 1, 3, And you can write your denominator here. You can delete this and it will find your root locus again. You can find it with, you can define your system in different ways in here. So any question? How we find the root locus? We just use our locus function, and inside we define our system and scale our graph in a y-axis, and then we just plot it. All right. So here, let's say you can just write double percentages and root locus. You can separate the inner sections too in your live editor. Second one, let's say plot grids, polar grids. Okay. So how we find our polar grids? Now, first you are going to define your numerator, denominator again. Okay. So now you are going to define your k variable, which is, let's define with 0, 0, 1. So now we're going to define R with capital. And then we're going to take root locus. For taking the root locus inside, you need to define your system again, your numerator and denominator, and with your variable k. Okay. So now you can plot your root locus function for polar grids. Inside, we can define it. We define our root locus as R. All right. Here will be our root locus. Okay. So after that, you're gonna define your scale with the v-axis. So let's define our scale. Two. Correct. And then you're writing your axis, z-axis. Axis will be in square shape. And now here with the S-grid, you're gonna put our polar grids on the root locus function. So for that, you're gonna define your system again. So for the polar grid, you write S grid function and you define your function inside. And you add your grid. You can add titles here again. Inside title, we can write root locus polar grid. So here with GTEx, you are gonna plot your omega damping ratio in a root locus function. So the first, let's say for the GTEx, what was our omega in this function? You remember? Yeah, anyone remember what was our omega? Anyone remember what was the omega, guys? Okay, let's first clear it. And then we can run the section. Yeah. Axis C. And axis B. Yeah, this is root locus polar grid. As you can see, we define your omega. Omega is your damping ratio, guys. Don't forget it. And we defined it for omega equals to 2, omega equals 1, and 0.5. See here, this is your omega equals 2 for 1 and for 0.5. All right. Okay, now. Okay, any question till here how we get root locus of the function? How we find the poles and zeros? Okay, let's go to the last part. Anyone don't remember for the homework last week I gave? I want you to define a function. Doesn't matter which one will be, it's up to you. Define a function. I want you to find the transfer function of it, steady state, and I want you to draw a step response and ramp response of your function and send it to my email, all right? Okay. Okay, now for the last one, we're gonna define our k value. K is our gain, so we're gonna define our k for our system to be steady state, for a steady function. We're gonna define our k, which will be which help our system will be steady. Okay, let's first define our numerator and denominator again. So, you can define your system like this: your numerator, and if your denominator convolution of two vectors, you can just use the conv function to get the convolution of two vector, and then you're going to define your R root locus again. Inside, you're going to define your numerator and denominator. You're going to plot your R. Define it as a root locus. Here with this, R will be a root locus of your system. Okay. Now you're going to define your scale again. Axis V, then axis shape will be square. We can add title again. Locus K value, you can write it. Okay. Now let's add a name to our X and Y label. For our X label will be real axis. Yeah. And Y label will be our imaginary axis. Yeah. So here now we're going to define our K value for the locus diagram. Inside you just write your text for the 2 value, okay, 2.6, comma, and your K equals to 435.7, let's see. All right. For your other K value, now we're gonna see the diagram. 2, comma, 1.6, comma, and for the K equals to 23.3, let's say. For your other K value, 0.7, comma, and your K equals to 0. Okay, now here you define your k value, and we're gonna find how it affects our root locus. For that, we're gonna use gtext, which show us the zeros. We define it as O. Now the gtext X will show us our poles. So this gtext for the first text will show us our zeros, and second one gtext will show us our poles for the k equals to 23.3 value, and for the last one for k equals 0, we can define our x for the poles. Right. So let's first clear it. Then now we can run the section. Yeah. See, for the k equals 0, here are the poles. Here is the poles. For k equals 23.3 and 35.7. Okay, guys, any question how we plot the root locus for the k value, your gain value for a steady system? Okay, let's take a look at another example here. You have control system designer, which you can see your root locus and your step response. In here, you can you can add zeros and poles. Let's say we add it here, and we see the step response, and you can shift it to see the step response changes. In here, you can modify your system. Let's say make it 10, so you can see our step response. It's not very good step response. You see, it's very stable. It's not stable. Let's increase it to 20. Yeah, it's more likely. Okay, in here your G value are constant, so we can see your amplitude. Let's make it 10. See a better step response. So here you can add zeros and poles, so we can see the step response. See, in here our step response is not good system here. So when we add zero a pole in here near the origin, you see our step response going to more steady state. If we get closer to origin, you see the overshot is too much for us here. So we need to add the pole somewhere here. Yeah, you see the change in the step response. So this is the overshot that we don't want. So we need to, you can change your pole position here to see the step response is in a more steady state. See, we can observe it from the root locus editor, or we can just, and you can define your system with the codes, and you can also plot it with the codes. So I hope everyone understands how we get our root locus. First, you define your system inside, and with the root locus function, you can draw your root locus. All right. In here for polar grids, you define our root locus function as R, and you're gonna see for the omega values, your damping ratio. And lastly, you are gonna add root locus function and plot it for the k values, your gain value. See how it affects our steady state for the function. Any question, guys? Okay, I'm gonna take the attendance list. Don't leave. Okay, that was it for today. Next week will be our last lab. So there will be a little quiz. I'm gonna ask you about from first lab to last lab. Just take a look from the previous notes, all right? Okay, see you next week, guys. Have a nice day.